Hi, everybody. This is the Physics of Bitcoin show. I am here with my co-host, Stephen. Today is July the 30th, um, and this is episode 28. Am I right?
Correct.
Yeah,
28.
28. So we always make a little introduction about what the show is about, for maybe people that have just joined. Um, it's basically we are two physicists. Me and Steven have PhD in physics. We have some eclectic career where we started, from the topic of astrophysics, where we did our dissertation, and then over time we changed subjects. I went in the field of neuroscience. Steven focused more on computational problems, um, computers, supercomputers, and things like that. And the idea behind that is in this changing of career, we brought with us our understanding of the world through physics. And we were successful in doing that, right? In see how powerful this concept from borrow from physics can be when you go to another field and you look at things in a slightly different way. In my case, for example, I was able to get a patent within a year of joining this new field, where I was an amateur, basically, almost. And this because I saw things with this angle of physics that gave me kind of an advantage, right? And some similar things with Stephen. He can tell more about this. But and why this is relevant for Bitcoin, because basically we are doing the same thing with Bitcoin. We are bringing this tools from physics, this understanding, this framework, because it's not just about tools, but also a way of seeing a phenomena through the light of science in general, mathematics, but in particular, this idea of physics where the main goal is to find mechanisms. Why we ask not just how things happen, but also why. We are trying to find the root causes for what we are trying to understand and study. So we want to bring this particular angle to Bitcoin, and we have a guiding principle that is Bitcoin is following this power law, is a network, but we are not just focused on that. We come up with different ways. One of the good things about this show is basically we are introducing new ideas, new ways of seeing Bitcoin that are very unique, and many times we give you kind of the first look at these breakthroughs or these new insights about Bitcoin. It's we're not just using things that other people have already developed, but we are coming up with new ideas that if I don't know of almost any other Bitcoin show that does that, right? It's like, I don't know if people appreciate this fact, but and we have kind of a vision of where we want to go. We are in the process of creating an institute to study Bitcoin scientifically. We will update you later, as things evolve on these. But yeah, so this is what the show is about, and every week we cover different topics. And in a moment, we're going to see the agenda for this particular episode. Do you want to add anything, Stephen, or elaborate on what I just said?
No, I mean, it's just you hit the most important thing, is that we try to get to the why. It's not just the what and how, which people often do in the financial modeling world statistically, right? But statistics typically does not get you directly into the question of why and the deeper mechanisms, and we're looking to understand that, and we do that to build our own confidence in things, as well as to try to simplify it a little bit and present it to you. And I do think we provide more new ideas per week than just about any channels on this topic.
I agree.
Yeah.
All right. So, okay, having said that, let's go ahead with the topic for tonight.
Okay. As people who follow us regularly know, we've taken a break for a couple of weeks I was on vacation with the family. And so getting back into the swing of things, this is a little bit of a hodgepodge of different topics. I call it some musings. But a general theme is that knowledge is power. And this is Francis Bacon, who is basically made that, wrote that statement, but in Latin, knowledge is power. And which is, I think, Centum es Podesta. Do I have that right, Giovanni? And, that's kind of an underlying theme for us, right? In our attempt to gain more knowledge about the mechanism, that gives us some power of understanding, and it turns out that mechanism is a power law. So that's the theme this week. Here's some various topics. Most valuable software ever? Question mark. And I think the answer is probably yes. But certainly one of the most valuable software systems that's ever been created. And in terms of the initial code, line for line, really the most valuable. I'm going to look at some very crude modeling of power law just with looking at the 4-year candles and then only the yearly lows. And from those, you can, determine what the power law index is with reasonable accuracy with the lows and the highs, but you see some variation, but they're around that, the core values that we get with much deeper statistical studies and with a lot more data. And then I use a different technique from our usual one. In terms of, Newtonian physics, we talk about position and velocity and acceleration. And we normally derive the power law where it's like a position versus time, where P is price is like a position. And we just regress that equation. But it's possible to also use a velocity method, which is, how much the price changes per time interval. So I'll take a look at that, and you can get a relatively similar measure with that method. Then a little bit of an aside. Recently, Udi Wertheimer, who's pretty well-known channel and kind of a participant in the space, an influencer, spent $3,000 to ask Grok 4 Heavy how high Bitcoin would go this year, and I've got some comments on that. And then some presentations of log periodic power law. Now, the ones that we've shown you in previous shows have usually been the typical 7-parameter method that you use to measure bubbles that happen over relatively short to intermediate timeframes. And it's suitable for looking at the Bitcoin bubbles that, will rise over a couple of years time frame and maybe crash over 1 year kind of thing. But you can also use a modified version that was developed by Sornet, DDA Sornet, that has 8 parameters, but it's intended to try to look at very, very long-term developments. And I will show that applied to the Standard & Poor's 500. He had originally talked about this in his 2003 book, Scale. 2003 book, Why Stock Markets Crash. You can see I'm coming back from vacation. And he applied that to the S&P, 22 years ago. Well, I'm going to update that with what it looks like now with nearly a quarter century later. And there's a kind of interesting idea that he presented there, which is holding up. Then the question is, well, can you apply that to Bitcoin long term? And I'll show why you cannot. But then I will look at the Bitcoin log periodic power law on shorter time frame for this particular cycle and how that's looking right now. And I've got a liquidity chart from Fidelity, and I've got some sort of coarse power law fits to how the Bitcoin treasury companies are growing. So let's jump in. First one, just one slide on this. The most valuable software code ever is the question. And this is a summary table from chat of what it said were the most valuable codes. It mentioned Windows and Office. It mentioned Google Search, the Android platform, OpenSSL, Apollo guidance computer. Bitcoin is the most disruptive. And of course, AI, GPT, transformer-based models for the future. Well, Windows, and I don't know whether this includes the Office revenue or not, but Windows was 2 trillion of revenue over 3 decades. Google search has led to 2 trillion revenue over a similar time frame, 2.5 decades. Bitcoin has reached 2 trillion market cap in just over a decade and a half. So, and the initial code was, I think it was 40,000 lines, and it's now grown to about 10 times that, but it's really a small amount of code initially. This one is just taking the block year candles and just pulling the data off that chart. You can start to show that there's power law behavior. But even before you do that, before you do a regression, you can just look at the chart visually. So on this 4-year chart, you see that the candles are getting smaller from one to the next. Each of these is from one halving interval to the next. So technically it's 4 block years, although after the second halving, there's not much difference with a calendar year. You can see that each candle is smaller than the prior one. So the volatility is clearly going down. And this is a log linear chart, log of price versus linear time. And you can see that it's curving over. It's not following a straight line as an exponential would, and as most financial assets tend to do. So the volatility is way down. You just see that by the size of the candles having shrunk. You know, you can't use the last one because it's a partial candle, but a factor of 3 or so just in log space, which is a very large number. And so there are a lot of times you will see people trying to make analogs with previous bubbles, going back to 2013, very often 2017 and 2021. Making analogs with those is wishful thinking because the volatility was much higher. If you just take the lows off that chart, you find a power law of 7.2. And again, the fifth candle is just, a year and what is it, a year and 4 months now. If you take the highs, you see a power law of 4. That's the flattening. But the average of those two is 5.6, and that's right around what you get. If you do a regression in block years, you get about 5.5. If you take those two lines on the big chart, they cross over, and they cross over at around age 27. Block year 27 is really more like calendar 28. So around 2036 or 2037, they cross over around 1 million. It's kind of interesting. We expect 1 million to happen prior to that, but that's roughly the time when you probably never go below 1 million again if you're on the power law. And we see that from the next slide, where we fit just the yearly lows. So now we have a few more data points, 15, 16 data points, and not all are shown here. I just show $100 and above for clarity. But you see, you see a dozen data points and the fit to all of them. And the slope is on the lows is a little bit higher here. It's 6.3. And the level of 1 million for a low is in 2035. So if you look out, that's age 26 on this chart. And 300,000 K is a low in 2030. So that's suggesting that we won't see prices below 300K once we reach 2030, and we won't see prices below 1 million by 2035. And then the little chart up above, David Nelson wrote a post where he also fit the highs. So the blue curve is kind of an earlier version of my low curve here. He's plotted it in linear terms, and so it's curving upwards. And he added the highs. And so you see the million from the highs hitting in the 2032, 2033 time frame, and then again the 2035 time frame for the lows. So a lot of space opens up in terms of real dollars, but in terms of relative dollars, volatility is still going down. Okay, this one is the power law technique from velocity. So normally we say price is equal to some constant times the age of Bitcoin from January 2009 raised to the power K. That's the power law index, and it's the steepness of the power law. And, we just fit directly that equation by taking the log of both sides, and then you have a linear relationship. But you can also differentiate, and that tells you how fast price grows in relative terms, in absolute and in relative terms. If you differentiate and then divide by the price equation, then you end up with dP over P, which is the fractional change in price is equal to the power law index times the fractional change in age. And so the price change is observed, the time change is known, and then we can measure the power law index through this method. So it's an alternative to taking ordinary least squares or doing quantile regression on the first equation here. So just to note, if the price change is 50%, the amount of time that it takes is 50% divided by K. So if K comes out to be 6, then you only have to change in age by 8% to get a 50% change in price. However, that's a percentage change of a longer and longer age. So it takes twice as long for a certain percentage price change when Bitcoin is age 16 than it took when it was age 8. So 50% if K were 6, 8% would take a year and a quarter currently, and when it was age 8, it would take a little over half a year. Okay, and the little chart at the top is kind of a ChatGPT view of what these different techniques are good for. Both the OLS and the QR are essentially the positional compared to velocity, or just the straight price rather than the change of price. OLS, good for the overall baseline and global. Quantile technique for the core trend estimation, a little more robust to bubbles. Both are pretty stable. The velocity technique is more for tracking change in over time. It's not very robust to bubbles at all, because it really, the bubbles feed into the change in velocity. And so it's, stability is variable. But with filtering, you can get a pretty decent result. So in the left-hand chart, what I did was I created 4-year windows, and then I calculated the velocity-based power law with the velocity method, the power law index. And you can see it jumps around a lot. That's the orangish line. It's quite jagged. It drops down to 3, it goes up to 10. You're seeing the bubbles come into play. But then if you do a 4-year lagged moving average of that, then it settles down, and you're pretty much in that space between 5 and 6, and you're confirming what you get by the other techniques. And right now it says 5.5, so it's pretty spot on there. You can do it in another way, which is you can just say, let's measure the total range at a given date and say, what index would I get? Just using essentially the endpoints with the velocity method. And again, it jumps around a lot, but then it stabilizes by around 2016, 2015, so about a decade ago. And it mostly bounces around 6, and it's right around 6 now.
This is extraordinary because one of the things that we do to sometimes to eliminate spurious trends is to take derivative, right? You're looking at the change, and to see that actually you recover the power law from the derivative. It's a strong evidence that we are talking. It's not a spurious trend. It's a real pattern in the data. It's
right.
It's no noise,
And so, it tells us that we have a pretty good handle on how much price will increase and how much capital needs to inflow as well to
Yeah.
sustain the power law.
And how difficult it is to change all this, because the fact that it's stabilizing over time, it tells us that actually Bitcoin has some kind of pattern or mechanism that creates these long-term trajectories, that if anything is becoming stronger, that there is more inertia, and it's more difficult to change it. When people say, "Oh, we are another regime," they don't know what they are talking about. At the end, they didn't do the homework. They don't go and look at the data. They make it up, but they come up with stories. We look at the data. It's no,
Yeah.
we don't make up stories.
Not narratives, interpretation of reality.
Interpretation is important, but based on real data.
Real data. We're interpreting reality. We're not writing narratives. Okay, here's a narrative from Grok 4 Heavy. It forecasts 400,000 K for November 2nd, 2025. So AI is better than us in a lot of domains, but right now it hasn't caught up to us here. Udi Wertheimer spent $3,000 to use the Grok Heavy and to get this result. And what's strange is I asked regular Grok a couple of times, how did Grok 4 Heavy do that? And the first time it said it used the power law model as baseline, extrapolated from Giovanni's framework, predicting 150K baseline by November, and then it overlaid a halving bubble cycle, modeling LPPLS for log periodic oscillations and decaying volatility with all these peaks. So I think it was modeling. My deduction from that sentence is that it was using the 8-parameter long-term version of log periodic power law, which I'm going to talk about. And then it says this aligns with post-halving patterns, ETF inflows adoption, blah, blah, blah. Well, that's pretty clear statement. But then when I asked it later, it didn't say that at all. It said, oh, Grok 4 used what somebody else asked, and has in the lower right. It basically said, to me, it said, based on ETFs and institutional inflows, I came to that. And then I asked Grok, what do you predict? And it said that, it predicts that's unlikely to get to 400, and it predicted, 150 to 200,000. So there's a lot of disagreement between Grok and Grok Heavy going on here. And Grok wouldn't give me a straight, consistent answers when I asked it multiple times. Just to refresh what I predicted by looking at the core power law trend plus the bubble mean and the bubble volatility, by the end of the year, a 1 standard deviation in the bubble space would be 185,000, and a 2 standard deviation would be 234,000. So, that's sort of the 200,000 domain, certainly not the 400,000. And I will show you the log periodic power law latest modeling, and that's much more conservative. It doesn't reach anywhere near 200,000. So this is my optimistic forecast, and the log periodic power law analysis will be the more conservative. So I thought that was kind of humorous. Okay, this is the very long-term methodology for log periodic power law, and it's in Sornet's book from 2003 as to why stock markets crash. And he talks about a singularity in the year 2050, and he bases it on S&P 500 price history. And he's basically talking about it in similar terms to Ray Kurzweil's singularity that, Ray has been predicting for decades would happen in 2045, and he has not changed the date. 3 decades ago, I think, or more than 2, he was saying 2045, and he's still been saying 2045. So I revisited this with another 22 years of data, and I refit it, and it says 2050 still for the critical time. You'll see on the right-hand side of the slide, the 8 parameters. So the new one is the final one. That's C1. That's the 8th parameter. And that actually is an exponential kind of term. Now,
so this is actually a super exponential, right?
This is super exponential because, it hits a long-term critical bubble.
Mm-hmm.
So it goes vertical. Now, the total range of this chart is a factor of 40 million times on the S&P, and 250 times of that is in the future. So 150,000 roughly of that was already in the past, from 1925 until now. So there's 80 years of past gave us 150 or 160,000 times already. And then this would say there's another factor of 250 ahead with it going critical. And what does it all mean? I don't know. It's an interesting question. But Bitcoin on the power law should be of order 10 million by that time, which is 200 trillion. And that's large enough for it to be dominant in a monetary system that might have global wealth of around 3,000 trillion by then. And right now we denominate all global wealth of about 900 to 1,000 trillion. We denominate it with a little over 100 trillion of global money supply of all the various currencies, obviously dominated by the dollar, but also the euro, the yuan, etc. So Bitcoin has, that's kind of interesting that when Bitcoin is in a position to change the monetary system potentially, or to become, the fundamental monetary technology and asset, is kind of similar to this time frame for the S&P to go singular. Okay, so then the obvious question is, well, okay, can I apply this same technique to Bitcoin? The answer is no, and I'll tell you why. And I kind of got onto this because I saw one of these other crazy curves where they use like a hyperbolic tangent kind of function. And they say, well, now's the time to take off. And, we're going to have an inflection. We've been curving over, but tomorrow it's going to inflect upwards and it's going to go hyperbolic.
Oh, yeah.
And you see this all the time. And, this is plotted on a log linear chart. X is where we are right now. So they've artificially added future bubbles, right? Those aren't real data. And so my question or statement, my question is, give me just one reason why it should have an inflection right now.
Exactly.
And hyperbolic delusion.
Wishful thinking.
Yeah. And it breeds complacency of two sorts. One sort is it encourages people to think that if they just have 0.1 Bitcoin, that's enough.
Yeah.
Right?
Yeah.
And also, when it doesn't happen, it increases the risk that they kind of panic, right? And sell because they say, well, this prediction didn't happen, so something wrong with Bitcoin. Well, there's nothing wrong with Bitcoin. There's something wrong with the hyperbolic model and with promoting delusion and fantasy.
Right.
Okay, so, but just for fun, I took that 8-parameter model and applied it to Bitcoin's monthly price history. And what did it do? Well, it went critical. And in fact, it wants to reach 100 million price, which is, log 10 equal to 8 on this chart, before the end of the decade. But 100 million price for Bitcoin would be 2,000 trillion market cap, and that's double all global wealth today. It also gave a critical time of 2040. So this is overfitting, overprojecting, not physically motivated. The additional term, the eighth term, looks like log of price times some constant times the age of Bitcoin, T. And so it's an exponential factor. And then it compounds with the critical time, and they actually reinforce each other. And so it goes super exponential.
Yeah.
So it can work for exponential assets like Manhattan real estate, which, everybody says, well, in fact, Saylor says, you're getting in early like Manhattan.
It's not.
Okay.
Yeah.
Manhattan is 6.5% compounded annual growth over centuries. Yeah. We're doing much, much better than Manhattan. So you don't want to do this for a power law network, at least not with the raw form.
Yeah. You cannot have both ways. You cannot have an asset that goes up 45% a year right now, and at the same time to have these constant in time. You can have it. You can have an asset like Bitcoin that was going up 100% in a year early on, with the price that there is a decay in performance. That is actually a feature and not a bug. So that actually kills the complacency, because it means that you should have invested in Bitcoin 10 years ago. Because if you have an exponential growth, it doesn't matter where you join. You're going to, of course, early on you get more years, but in general, it doesn't matter in terms of the efficiency of your investment. You can join at any time. It's going to give you the same efficiency, right? In terms of annual returns. The annual returns don't change, are the same. That is what an exponential is. But with something like a power law, your annual returns are going down. So it's important that you join in early. And so when people say you're early, no, you should invest now, because you already lost 15 years. Any years that is going on, you're going to get smaller returns. So it's important that you do it now.
Yes, but it also becomes available to more people because the volatility's gone down, and most people are pretty risk averse, right?
Yeah, so you're scared of it. Yeah. But right now it's kind of almost perfect, because you're still getting pretty good returns of 45%, right? And it's not that scary. It's still very stable, relatively stable. So it's perfect time to join.
So here's what people really want to know, which is what's Bitcoin going to do this year. So this is the usual log periodic power law model with 7 parameters, not 8, so appropriate for shorter intermediate terms.
Yeah.
And I mostly ran on Chat GPT Code Copilot, but I also ran on Grok, and it agreed. It gave the same answers. And I ran both.
Did you simply ask to apply the log periodic power law to the data?
Yes.
And really and you gave it much data, 2.6 years?
Yes.
Yeah, okay.
Yeah. And so 2.6 years I chose because basically the price started rising. 2022 was a down year, and the price started rising right at the end of that year, beginning of 2023. And so it says A equals 141K. So that's kind of the maximum that it's projecting. And it says that the critical time is 989 days after January 1st, 2023. That translates to the middle of September this year. The R-squared is very good, 0.96. The RMSE error is 6K, so it's a very good fit. And the estimated price 2 weeks before peak, it's difficult for it to really estimate close to the peak, is 131,000.
Yeah.
Now, if I run
this could be also that there is a correction and then we continue to go up, right? It doesn't mean that is a huge big correction and it's the beginning of a bear market, but some big event is going to happen by November, right?
I'll talk a little bit about
September
correction, but it's hard to. So then I also ran it with just 1.6 years of data, chopped off 2023. It gave the same answer for the critical time.
Yeah.
R-squared was a little lower, but still good. but the estimate was lower, is 118,000.
Okay.
And then I also ran with 0.6 years. And so now I show all 3 stretches of time on one chart.
Yeah.
And this chart is only for 2025, so you can see things more clearly. And the shorter the time frame, like the 2025 only, is the red line. So it waves around more. It's sort of like particle trapped in a box, right?
Right.
It has to fit it within the walls, and its walls are closer in. And the other 2 lines are from 1.6 and 2.6 years. So the one that only used 2025 data estimated a price of 130,000. So it tended to agree with the longest term one. And if you take the average of all 3, you're sort of at 126K plus or minus 5K 2 weeks prior to the critical time. And as you get closer and closer, you might want to use, hourly data to do the modeling.
Right.
Okay, so then the question is, if you get a crash, how big is it and how long is the recovery period? So looking historically, this is checking the z-score. So how big was the bubble relative to the standard deviation of all of the price up until that point? So this shows the 3 bubbles of 2013, and the recovery periods is the length of the thick line. And then the z-score is, how big the bubble was, essentially, in standard deviation terms. So the first 2 were around 4, z of 4. The third one, the 2021 bubble, was around z of 3. And you see the recovery periods have gotten shorter. And then I asked chat to estimate how long would this recovery be. And, I kind of worked with it as to what the z-score would be. It should be around maybe 1.6 because volatility has come down. So I kind of gave it what I thought the z-score should be. And then it said the recovery would be 11 months. It would actually be less than a year. So just like the volatility getting shorter and the peaks relatively less high, then it's easier to recover, right? So the recovery period in 2026 could be under 1 year to get back to the prior high. That's what the recovery period.
Yeah, that is what you mean by recovery. Okay.
And here I set it at the optimistic 140K. So that
does it tell us where how much do we drop?
Yeah, I asked about that and kind of talked with Chad about that. It suggested something like 30%. I thought was too conservative. So I think really what we look at is the power law core, that it's going to drop back to the power law core. So what you do is you calculate where the power law core will be, and that'll be like 75, 80,000 if I recall correctly.
Yeah. Yes.
Yeah.
Well, I will not complain because there are a lot of opportunity, for options, all kind of things. If you have a clue of what is going on.
Yeah. So if you know how low and what time frame, you've got some guidance.
Yeah.
This is the latest from Fidelity on the global money supply measure of liquidity, and I note that liquidity is only up 10% since the beginning of 2022 because actually the American money supply dropped for a while there, which was highly unusual.
Yeah.
But we're back into pickup mode, and particularly from the beginning of 2025, it's been picking up. It's the orange line here, and you can see it's relatively steep, growing from, well, the low of this is something like 70 trillion global M2, and now it's 114. And you can see that it's picked up by something like 10 trillion since middle of last year, roughly in the past year. So So that's good because it leads by about 1/4, 11 weeks, 13 weeks, something like that. So far liquidity is looking supportive. And I'll close with just a little bit on the treasury companies. Now, this is not the treasury companies. It includes the treasury companies, but it also includes the ETFs and a lot of exchanges and mining pools, et cetera, and even some corporate, some government holdings. So it includes Satoshi's coins. It includes the coins yet to be mined. It includes Coinbase, BlackRock, Strategy is only number 5 on this chart. Binance, Bitfinex, Wrap Bitcoin, the Fidelity ETF, and the U.S. government holdings as the top 10. So I said, does this look like a zip rank distribution? So we've got the Bitcoin held on the y-axis. We've got the rank on the x-axis. We've got 44 entries, and it's roughly a minus 1.26 power law. It flattens at the high end, as you would expect. It's pretty hard to get to, 3 million. I don't know if anybody's going to get to 3 million.
Yeah.
Maybe the U.S. government could do it. Maybe Saylor could do it, but there aren't many that could get it to 2 million or above 10%. So you expect a flattening, but the rest of it is fairly good fit to power law. And I think I don't have it written here. I think the Gini coefficient was in the 80 something percentile for this.
80 percentile?
Something like that.
How that compares with Gini coefficients from
high 80s, which is quite unequal.
Yeah.
Yeah, a high Gini coefficient means it's quite unequal.
Can you tell us about the Gini coefficient? What is meant? How it's calculated, or what it's supposed to represent?
Well, it's just if you have a power law that's, I'm trying to remember the math. It's like,
but what is supposed to represent?
Well, what it represents is
I know what it represents.
The inequality of the distribution,
right,
of whatever it is. So it could be wealth or income or Bitcoin, or you could be talking about the sizes of lakes,
right,
in some countries. So it's a measure of how flat or steep the curve is, and if it's steep, it's a high Gini coefficient, which is a measure of high inequality. And in some cases, the Gini coefficient is not calculable in the normal way because it's defined such that it doesn't exceed 1. And so you can get distributions where it kind of doesn't apply.
Mm-hmm.
But the general idea behind ZIP is that you get a power law that's kind of like around -1. A ZIP law is actually got a -1 slope. Right. So here we've got the treasury holdings, the top 100 companies, and I've got it with and without strategy included. So the top one has strategy included, and you can see that that point is sitting way up there at close to 700,000. And in that case, and you have to use 2 segments because you just cannot fit it, the whole thing with a single power law slope. So the first segment is a -1.28, and then the second segment is much steeper because we've got all these new entries, and they don't hold very much. They have 100 Bitcoin, 300 Bitcoin. So it's really crowded down there, and they have a lot of work to do to kind of catch up.
Yeah.
If they're going to be viable, they need to get up towards the blue line slope rather than be on the slope that they're on. The Gini coefficient for the blue line slope is, the Gini coefficient for all the data, actually, regardless of the slope, just throwing all the raw data and calculating it directly from the data set, is 0.91 with master, and it's 0.79 without master. So the larger chart excludes master, and so the fit on the first segment, the blue line, is a rather different power law. It's -0.69 slope up to rank 15, and then it breaks back to a similar -2.7. So we will see whether other guys, can get up on this slope and sort of be on the same slope that Master's on. But right now it's really broken out.
That's very interesting that there are two regimes. It's really cool.
Yeah, it is interesting, and it'll be interesting to see how they evolve. Now, this shows the growth of all the corporate treasury holdings in Bitcoin. And if you start from when it kind of took off and where you had more than about 1,000 or so, then you go back 5 years. And so if you use that as a starting point, it's kind of roughly a 2.5 power law. And it says that by 2031, it would amount to 10% of all Bitcoin. And by age, well, these is in quarters. So it would be 1, 2, 3, 4, 5 by 50 quarters with 12 and a half years after 2020 by, 2033 or late 2022 already, but 2033, you'd be at 20% of all Bitcoin would be in these treasury companies on that projection. Okay. And
now, one thing to consider is that they are single entities, but they really represent a lot of investors, right? It's not just one single investor.
Right.
So that at a certain point, maybe we should consider that, but yeah.
Yeah, and I did some modeling of that in a previous show and presented about how that changes the Gini coefficient and the power law chart if you reallocate that to the number of shareholders, for example, or if it's government holdings, the number of citizens. So it does make the distribution more equal.
Yeah.
And now, Vanguard has added Bitcoin into its funds. It's got like a total stock market fund that's now got strategy in it. So indirectly, it has added Bitcoin.
Yeah.
And so a lot of people are going to be owning exposure to Bitcoin, even though they don't realize it.
Yeah. It's unavoidable.
Yeah. So I'll close with the answer. Someone asked, name one thing more important than Bitcoin. My response was carbon. So I will close with that.
Yeah. I agree.
Okay, let's stop the sharing here if I can find my cursor. Okay, good.
Okay, great. I will share my slides. Let's see. Okay. So this is what I'm going to discuss. So I'm going to this very, very interesting adventure. Let's call it. Let's see if I can maximize this somehow. Slideshow. I don't remember what I did last time, but okay. Full screen mode. Is this better?
It's better, yes.
Okay.
Yeah, it's a good bit better. Yeah.
Good. Okay, let's start. So I'm looking at this idea, this concept that is probably not super familiar to a lot of people. In fact, even people that know a little bit of physics are still unfamiliar with this concept, even if it's becoming in modern physics is actually one of the most important core principle. I think it's an historical thing because physics, started basically with Galileo, Newton. They emphasized this concept of force, right? So force is basically this idea that if you anything that we observe around us is changing and is moving, right? In particular, if you're thinking about mechanics or how objects move in space due to some kind of a force, right? So now, of course, if the object is already in motion, it will continue to move. That is the idea, and it changes is velocity or its trajectory by a force, if a force is applied. But constant motion is almost like you're not moving at all in a certain sense. So any change in motion, anything that happens, in terms of events, there is some kind of a force behind. Most of the things that we experience on this planet are actually due to the electromagnetic force. It's surprising, right? It's just one main force. The light that we observe, that tell us about the environment, the fact that you can walk on the floor, that is due to the electromagnetic force. Most of the chemistry inside your body is the electromagnetic force. The other force that we deal on a regular basis is gravity. And then in rare occasion, we have to deal with nuclear forces, right, with the other two forces. But so you can formulate physics through this idea of a force that Newton told us is the product of mass and acceleration. So an acceleration basically is proportional to the force, but inversely proportional to the mass. Eventually, in time, this idea of energy was developed, right? That is related to the force, but it took time to be evolved. People can go and look at all these concepts. Very fascinating to study physics from an historical point of view. But one other quantity that it took even more time to be developed is this idea of action. Okay, so action, first of all, in physics there are quantities that are scalar, so basically we don't have a direction, like energy, for example. Force has a direction, right? When you talk about force, force points in a particular direction. So this it doesn't have a direction, and it's related to the concept of energy. In fact, basically turns out it's related to energy by I can show you here. It's energy times time, basically, right? So energy is force times distance, and action, it's energy times time. Now, power, that is another concept. Basically, how much energy per second is used by some system, by a machine, for example. So if you take energy multiplied by time, so it's how much energy is applied in a system times the time that this energy is used or consumed by the system. Now, it turns out it's a very powerful concept because you can show that basically everything in nature tries to minimize, right? So you can think about calculating. So imagine you have an object that is moving from point A to point B. Let's see if I have a graph of that. I don't. Okay. But imagine you're going from point A to B, right? And there are many different ways you could go there, many different paths. Now, in nature, it turns out that there is one particular path that it depends by the environment, right? So if, for example, you could have empty space, in that case, you will not have what is called potential energy. So potential energy is basically the background energy that you have. Like, for example, if you are in a gravitational field, right? You are nearby the surface of a planet, or maybe you're a planet is nearby a star, and so there is a background potential energy. Or maybe there is a field, a magnetic field nearby, or maybe there is an electrical field. So an electrical field means there is some kind of object that is producing, as a charge, for example, and this electromagnetic field covers, it has a certain strength according to its distance from the source, right? So this potential energy will affect the trajectory of a of the object that is moving inside this space. And so it turns out that you could track all the possible paths that you can imagine, even paths that go very, very far away to another galaxy and then come back, etc. And now you calculate this quantity because you will basically do a calculation that looks like this. So you will calculate the kinetic energy, you subtract it from the potential energy, and you calculate the sum, right? You're going through this path, you can minimize the distance, you can break down this path in small little chunks, and then you calculate at every particular chunk, you calculate the kinetic energy, the potential energy, you subtract the two, and you sum, right? You sum all these little intervals over time. And when you do this, basically this is what the action is, right, for that particular path. So it turns out that, and we don't know why this is it, right? Why nature likes to do this. It's one of the biggest mystery we have in physics. It likes to minimize this quantity. So the path that come to, there is one unique path that minimizes this quantity, and this is what nature likes to do. Now, there is an interpretation of reality that is what Feynman proposed, is that actually the particle follows all the different paths. It doesn't follow one path, but somehow all the other paths kind of cancel each other. But we are not going there. You can look it up. It's called Feynman integrals, but it's a really fascinating idea. And by the way, this video, it's a very, very interesting video. I love this channel, Veritasium. The guy that does this documentary, by the way, is also a physicist, but he's focused more in teaching and sharing knowledge with the large audience. But I suggest you to look at this video. It's very interesting, fascinating video. And
Giovanni,
yeah.
Can I make a comment by way of an analogy?
Sure.
Sure. Everybody does this in their daily life. You need to go from point A to point B. You make trade-offs and decisions about how much time and how much energy you're going to expend, and that energy might be cost as well. So you might make a decision as, shall I drive there or shall I fly? And you're kind of trying to minimize the product of the time you spend and the price. Or you may make a decision about, you may be driving, but you make a decision to go this way or that way, and you may trade off time for paying tolls or whatever. So everybody in their daily life is trying to, at some level, optimize the product of energy and time together.
Exactly.
And so that's the least action kind of idea.
Yeah. And that is true. We don't know why nature does that, right? It doesn't have to, but it makes sense. It's logical, but nature somehow computes, there is some mechanism that minimize this action. And now the type of energy that we were discussing here, kinetic, is this what it means. Ke is kinetic, this potential. Kinetic, it's the energy associated with motion itself, right? It turns out that is the mass of the object multiplied the square, and then divide by 1/2. How that is derived is another topic, but that is how you calculate the kinetic energy. Now, the potential depends on what you're dealing with. Are you dealing with gravity? In this case, this will be the potential that you get by an object that is nearby the Earth. The G represents the acceleration due to the Earth gravity. It will be more complicated if it is a planet nearby a star or whatever. But near the surface of the Earth, the acceleration due to gravity, because gravity, remember, is a force. A force creates an acceleration. It's a constant. If you take a physics class, it's 9.8 meter per second squared. But and then it's proportional to the displacement, right? So how far you're going how far you are going from the surface of the Earth, x. Okay, and then it turns out, right, that motion of an object nearby the surface of an Earth can be solved. You can find the equations that describe a motion by minimizing these. And now this is, if you took any class, calculus class, you basically take the derivative of these, and then you set it to zero. That minimize this quantity. Minimizing a quantity, you do it by taking the derivative and setting up to zero. Derivative, remember, is the change of that quantity. So this gives you a background. And over time, this approach has been favored by physicists because it allows you, it's much easier to calculate the kinetic energy and the potential energy than resolving. So starting with F equal ma, then substituting what the force is and solving it with what are called differential equation is much more complicated. In particular, not for a problem like this where it's relatively simple, but if you have something complicated, you have a complicated field, or you have other factors, maybe different forces acting on it. It's really complicated. But if you're doing it in this way, it simplifies a lot. You can, these are things that are taught maybe in some advanced physics class or maybe at the graduate level, but they should teach it early on because actually simplify things instead of making it more complicated. But eventually, for example, when people talk about deep topics in understanding the most fundamental laws of physics, they write down what is called the Lagrangian. It is basically a derivation. It's a way of writing down basically the solution for this, right? So I told you take the derivative with respect to time because you have variables. You have you basically have two variables. You have this q that is basically the velocity and time. So you take the derivative with respect to both of these variables. And then you want to minimize this quantity that is called the Lagrangian. Basically, like I say, it's what you're trying to minimize the action. And writing down the Lagrangian for some kind of physics law, it's the secret in understanding how that law works. And so a lot of modern physics is about finding this Lagrangian for many different things, right? And then putting it together and maybe writing a big, huge equation with all these Lagrangian pieces that represent basically, you can write it on a t-shirt. It represents how everything works in the universe. Physicists are moving more and more in trying to explain the universe, writing down these Lagrangians, okay? So beside, the mathematics itself, so basically we are trying to minimize, we are trying to optimize, finding the optimal path for the object. And because nature likes to do this, like to minimize this quantity. Now, what is the relevance with Bitcoin? So with Bitcoin, I'm trying to skip some of these slides. I want to show you and define these. I'm applying these to Bitcoin. What we can do, so because basically it doesn't matter what you're trying to minimize, what are the variables that you're trying to minimize, right? So if you're dealing, for example, with velocity and position of the object, your variable will be the velocity and x, right? And so there is this variable x, the velocity is the derivative of this variable x. So you can rewrite this equation in this way. And now, what is the application of that to Bitcoin? Well, we can try to find some variable, Q, that represents some relevant quantity for Bitcoin. So in this case, for example, we know that Bitcoin is a power law in this space of price and time, right? These are so we are not talking about the law, the position of an object in space. We are talking about some other parameter that we want to understand, and we want to apply this same principle. Is there some kind of minimization of optimization of how the price evolves in time, right? So it's similar idea, even if not one-to-one. We are not talking about a physical velocity. We are talking about something similar to a physical velocity. In this case, and we could do it with users, with hash rate, but let's focus on price, that is one of the most important quantities, right? So I'm going to redefine, I'm going to create a new quantity, a new variable that is basically the logarithm of a change in price. So basically it's the return. So it's the logarithm of a return, right? So if you have price at time 0, and then you're interested in what is the price a few years later, and you take the ratio of these, it's basically your return, how much more you gain by holding Bitcoin. So this quantity P over P0 is this return. And then we know, because everything about power law is basically working in this space where we are interested in the scale, and the scale is given by taking the log, right? So instead of focusing on the change in price itself, we're focusing on the log of a change in price. So I'm defining this new quantity that is a log of a returns. It is actually, by the way, a very commonly used quantity in finance. And then I'm defining kind of a new time that is the kind of a renormalized time, where I'm taking the change. How much time did it pass from time 0, when I measure the first price, and time T1, the future price. And then I take the log of that, because we know that somehow there is some kind of proportionality between the change in price and the log of a change in price and the log of a change in time. Okay, if you do that, and now you're substituting in this Lagrangian equation, right? That basically you're trying to minimize this quantity. In this case, you see, I'm taking just the derivative of this quantity Q relatively to this new time. I take the square. This kind of looks like the velocity, right? Because it's basically I'm measuring a change in this quantity Q, that is kind of the velocity. Remember, if we go back to the Lagrangian, like this one, right? It's the kinetic energy, so mass times velocity square, 1/2. So this is the equivalent of that, 1/2. Now, mass, I could introduce a mass, but it's going to be a relative kind of arbitrary number, M1. It will be, if you add many different things to compare, maybe mass was relevant, but here it's not, right? You can make mass equal to 1. So it's not an important parameter. And then you take the derivative, right? You take the integral, so you're summing these over these changes in the log of time, the ratio of the log of times. Now, you may notice that there is not a potential here. We could introduce it. That will be that will be the next step. What is a potential, right? You could think, maybe is a change in liquidity. So it's something that I want to discuss with Stephen. Maybe we can make up some interesting or relevant potential that represents how the external world interacts with Bitcoin. Here is more like if you're looking at something that is neutral, where Bitcoin is not really influenced too much. It's all internal dynamic. So like a particle moving in empty space. And so then, you apply this Lagrangian, you're taking the derivative with respect to time, with respect to the velocity itself. This is how you write this equation, and what you get, you recover the power law. So this is basically showing that if you start with something like this, and you apply these equations, that are the typical equation that people try to solve in minimizing S, you get a power law. So the power law is almost like some kind of a geodesic, right? Also this principle, it's also related to the principle of a geodesic, right? When an airplane is trying to go through two different positions, it's not going to really on a flat, straight line. It's trying to follow the curvature of the Earth to minimize the distance on something that is spherical. So basically, this shows that the minimum distance in a space where the logs of a scale is considered, it's the power law. It's a it's almost, I don't say a triviality, because we know that we get a straight line, that the power law is a straight line. So a straight line is a geodesic in that space, but it's cool to see it derived in this way, like starting with this principle of least action, least action. But now this also gives us a tool, because we can try to calculate this quantity. And so what I did basically this experiment. I draw in this space, right, in the log space, I draw many, I ask the code, I wrote a code where I create many different paths, Here I'm selecting some of these paths, but there are paths that go above the power law, paths that go below the power law. I draw thousands and thousands of random paths. The requirement is that they start from where Bitcoin started, basically zero, and they end up where we are right now, the price at this particular moment. And then I calculate this quantity that I just show you, that basically with integral, with sum, and that will be the total action. And these are all these dots, okay? And then I calculate it for the power law itself. And the power law, it's the minimum. So both in theory and through experimentation, we can show that following the power law minimizes the action. It's the smallest possible action that you can get in this space of log. So the idea will be this. If you are looking at a process that is scale invariant and that is a power law, and you're working in this space of a log of price and the log of time, then the power law is the path of least resistance. And anything else will give you a bigger action. So that means it's less likely. This is a part of it. It's the most likely path. Now, we know that Bitcoin, the real Bitcoin price, right, didn't follow perfect power law. So there are deviations. But this is why also it wants to go back to the power law, because that is what is the most likely the path of least resistance, in a certain sense, for a process that is scale invariant, right? Now, the next step will say, well, why do we have a scale invariant path in the first place? And I think that could be answered by introducing some kind of potential that makes sense. And then in that case, we show, even alternative path, like for example, an exponential or things like that, will not be the least, the path of least resistance. It will, even in that case, you will have a bigger action. So that is the next step. But this is already interesting. It's a very interesting perspective, right? It gives us more insight and more depth on why Bitcoin follows a power law in the first place. Okay, so this is it's some preliminary result, but this is what I'm exploring at the moment. Do you have any comment, Stephen?
Yeah, very interesting. I think the question around the potential energy component is what we have to think about is how does liquidity flow in? What are the channels? Because it's the liquidity flowing in through those channels that imparts momentum to Bitcoin, right? So we've got a momentum measure. And as far as mass and momentum, that could be the dollar, the unit.
Right.
Could be an ounce of gold, right? Representing
Yes.
the mass. But, the channels are really how is capital being raised by the treasury companies, for example.
Yeah.
So capital flows into the ETFs is kind of direct purchase. It flows into the treasury companies as they go out to mostly the bond market to raise money, right?
Mm-hmm.
And then if governments build up strategic reserves, they're mostly going out to the bond market too. So I think the biggest pools of capital are the bond market. Sometimes people sell stocks to buy Bitcoin. So to some extent, the equity markets. Sometimes people will sell real estate. But I think right now it's the bond market. Where on the curve, the duration curve, I'm not quite sure. Saylor just put out this latest one, which is like money market fund or commercial paper. So it's an alternative to treasury bills, short-term money, but he's also got longer term paper there.
Yeah.
So it's some integral over primarily the bond market currently, I think.
Yeah. So yeah, we can come up with a potential that makes sense, or maybe different examples, and say, okay, under all these conditions, you will still get a power law, right? Maybe with some general principle, like I don't know that um, maybe scaling variance needs to be invoked. I don't know if we can derive it from the potential, but yeah, it's something to think about. It's a very interesting thing because it will tell us that Bitcoin is doing what it's doing because it's really the best way for a monetary system, for an alternative monetary system, right? That is the entire story. We are seeing a transfer of wealth from the traditional financial system to this new system, and you want to do it in a way that somehow optimizes some kind of parameter, right? And it could be the time that it takes, or avoiding singularities. We could try to many different ideas, but I think it's a very powerful principle because it really goes to the core of using physics ideas, right, to describe how Bitcoin behaves. And there is no more core idea than the action principle in physics. And so it will be really powerful. I think I'm already happy with this result because basically saying if you invoke scaling variance, then you don't have an alternative. You have to go through a power law. And we know that Bitcoin didn't follow a perfect power law. So actually you can try to measure these deviations, but and why they are periodic and so on, right? So maybe that also means that there is some kind of a potential that changes in time, right? That is also periodic. Maybe during the bubbles are caused by a change in the potential that pushes the price away from a perfect power law. So it's a kind of a very interesting investigation path, I think. It gives us a language that we can use to try to describe many different properties of Bitcoin. But even if some things are after the fact seems not really trivial but expected, like for example the fact that all these parts, it was very satisfactory to see it happening through an experiment, right? Because people will love for the price to have done something different, right? But anything else will have actually made the action bigger. That means they are really unlikely, path. What we are following is like in fact, I tried even an exponential path from the start to today, and that also give us a very much higher action than the power law. And I suspect it's the same thing. If we start to leave a power law and we follow an exponential, the action will be much higher. So it's very unlikely path. It burns the resources, It doesn't use the resources in the most efficient way. So it's just a start. So it's something that it will be interesting to explore, and maybe we can do it together.
Yeah.
Okay. So I think we have a couple of questions. So, for example, Howen is asking this question.
Yeah, I'm going to share my screen to answer that.
Sure.
So this slide has actually, I've added the eighth term or the eighth parameter. So it's the same equation plus an additional term. So if you look at the ABC and the critical time and the M and the omega, and there's also a phase term phi, and you add those all up, that's 7 parameters. So that's the usual model. if you want to try to apply it over very long periods, then there's another term that goes like this: D times T. So it ends up, since it's log price, it ends up being an exponential term. So you just add that additional term and then, do the optimization in the multi-parameter space. So it obviously gives you exponential behavior, and then when it interacts with the critical time, then it goes super exponential.
Mm-hmm. Yeah. Okay, and then we have this other question.
Yeah. Well, I presented, I think it was in the last show, but in one of the last couple of shows, I presented the concept that these Bitcoin treasury companies have the opportunity to turn themselves from something that has corporate exponential dynamics into something that has city-like power law dynamics, and thereby making themselves much more Lindy, much more long-lived. Corporations typically will last a decade or maybe 2 decades. Very rare to last 50 years for a company. If you turn yourself into primarily a Bitcoin treasury company, you're going to behave like Bitcoin plus, some some alpha that you try to generate through financial engineering and issuing securities and using that to buy more Bitcoin. So underlying that, you're going to have a power law nature. It's sort of like power law plus whatever you can do on the financial engineering side. And so my expectation is that when companies get to a certain critical size of Bitcoin that they hold, and also you have to consider what percentage of their overall valuation is Bitcoin, then yes, they will start manifesting themselves more like long-lived cities. And I think strategy is already there. They're of a scale now of, similar to a mid-sized American city of 400,000 or 500,000 people. And so they've got the benefit of that. And other companies are I think that's where there's this rush. It's the same problem that Saylor initially had in 2020, and he realized that he was treading water, that he couldn't stay ahead, and he couldn't catch up with the AI companies because they had such a big lead. So he couldn't transform his, that would be the normal thing. You'd expect to transform your company to a new business strategy. But he said, no, I need a new finance strategy in order to get out of this trap of treading water and getting ahead of the curve. So he's done that, and others are trying to do that. And the top few will succeed, and a lot may not reach the scale.
Mm-hmm. Okay. All right, guys. If we don't have any other questions, got some compliments. People were missing us and things like that, but I don't see any other relevant question. We can adjourn the meeting and see each other next time in a week from now.
Thanks, everyone.
Bye, everybody. Thank you so much.